This is the type of ice table problem that requires the most thought and then application of understanding to actually solve. So what's maybe one of the first things that you should look at on any problem that says find the concentrations at equilibrium? Could be multiple good answers. K. The first thing probably should be, what is K? And is K either very large or very small? In this case, K is very large. The second thing that you might want to look at, and this is a little bit of metagaming, but look at the coefficients in the equation. I've got 2, 4, 2, and 7. Why is that important? Particularly thinking about the math.
Either going to add or subtract by the x of that concentration. Like if, for example, the COO, there's going to be either plus or minus.
Yeah.
2 of that, 2x of that.
Yeah. So like when we do, if we're doing an ice table, right, the change would be like either plus or minus that coefficient of x, but then when we put it into K, it'll be raised to that power. And I've already said I'm not going to give you anything more than a quadratic, so a second order polynomial. If you try to solve this as is, this will give you some x raised to the 7th, and then you'll multiply it by some x raised to the 2nd. And so you'll get a ninth order polynomial. So there must be something that I'm expecting you to do to reduce the complexity of this problem. Take like 5 minutes. Try to work out how you would start this problem, where you would go. And then if you get stuck, try to write down a question. This isn't a test, so you can talk to people next to you. All right, so that's about 5 minutes. If you really know what you're doing, that might be enough time to solve this problem, actually. Because even though I've got a bunch of these things that could turn into crazy polynomials, this should simplify pretty nicely. So what is the first thing that we want to do for this problem? Huh? Yeah. Why do we need to do limiting reactant? To what? Divide by the coefficients? No, I mean, well, why are we doing a limiting reactant ice table instead of a equilibrium ice table? We need to make something zero to make this problem simpler. Right? In order to do a small x approximation, I need to have something that is zero so that when I assume that my x is so small that it doesn't matter, I still have an x to solve for. Otherwise, we would cancel them all. Which way do I want to sort of push this reaction? Do I want as much reactants as possible, or do I want as much products as possible?
Favors products.
Yeah, favors products because I have a large K, very large K. So we want to try and push this to the right as much as possible. So that means we're going to be subtracting and adding according to the coefficients to get everything over to products. And here's where we would divide by the coefficients. Yeah. Are there any questions of how we got to making this decision? We're doing limiting reactant. No questions. Everybody's 100% why we're doing this? Okay. So then there's so many ways that you could try and figure out which one's going to be the limiting. This one is pretty easy because I'm mostly going to be using up Like this is a lot less, and it's also going to be divided by more. Another way you could do this is you could just try with each. So you could do 0.1 minus 4x, and I'm trying to make that 0. So 0.1 equals 4x, so 0.025 equals x. And then I say, am I actually able to subtract that much from the other thing I'm subtracting from? So subtracting 2 times that means I'm subtracting 0.5. So this is 0.65, so that's fine. This will be 0. This is plus 0.45. This is, 7 times. Point 775. And now we can do our second ice table. Because we didn't find the concentrations at equilibrium. In fact, we probably moved farther away from equilibrium because now I have a 0. But we're doing it with a purpose because the 0 means this will now shift to the left. So now this will be plus 2x, plus 2x, plus 4x, minus 2x, minus 2x, minus 2x. Oh. And this is good because now my K has already told me the reaction really, really, really favors products. And so whatever I'm going to be subtracting from my products is not going to be very much. In fact, it'll be so small that I can ignore it. And what I add to any concentrations that already exist is also going to be so small that I can just ignore it. So the only thing that I can't ignore is how much I'm adding to 0. Because 0 is nothing, and there's not really a number that's small enough that it would be insignificant. And okay, so this will be 1.4 times 10 to the 14. Now we just solve for x. Oh, and one of the things that happens a lot of times if you take shortcuts and do like I just did, where I could type all this math like this, divided by that, times this. It's all easy enough to do just in the calculator. It's really, really easy to forget that x is in the denominator. So I got 1.739 times 10 to the 15 equals 1 over 16x to the fourth. So I need to swap those. And actually, one divided by that times 16, 3.593 times 10 to the negative 17. And then I need the fourth root. I guess that's not the final answer, but did everybody who actually typed that in get the same thing? Or did I make a mistake? I think that's right. Yeah. Somebody came by my office while I was writing this, and I said, "What's your favorite number?" And they said 14. So just needed a big number. And now we should do a small x like the 5% rule. Check to make sure that this is small enough. So find the number that we're changing, or the smallest number that we're changing, like 0.45. And we'll do 7.74 times 10 to the negative 5 divided by 0.45. That's real small. So times 100, that's 0.017%. So very safe assumption. So my final concentrations will be, or even the, do this. ClO. Oh, wait, it's 6.8 times 10 to the negative 4. So really the only thing that actually changes is ozone, O3. Any questions? Yeah. If you can't plug in what? Which part? Oh yeah, so like you could multiply Yeah, you basically multiply this on both sides, so it's up here, and then divide all of this by that. And then you'll divide by the 16 and then do the fourth root. Yeah. In case you didn't know, it's like if you wanted to take the fourth root, it's the same thing as raising this to the 1/4 and raising this to the 1/4.
Like, if it wasn't like 17%, it was higher than 5%. What did it become?
Yeah, so if it was higher than 5%, then you would take the number you had calculated for x, and then you would have to plug it in. Okay. Then you would plug it back in. So here I didn't actually write any of the x's in, but all the places where we assumed x was going to be really small, I would have to plug in this x for those to calculate these numbers and then solve for x again. And then I would check to see if it changed by a small enough amount. And actually, I could go to a problem where we did that. The other trick then is that, so here I didn't change, because my number was so small, if I plug it in here, it's not actually going to change the number. So I didn't actually plug it in. If it's less than 5%, you can do that. If it's not less than 5%, then you do have to plug it in because it will result in a bigger change. Yeah. Oh, this was to check. That was to check the 5% rule. Oops. So I wanted to check if x is less than 5% of my smallest concentration up here. So 0.65, 0.45, 0.77, 0.45 is the smallest. And we just want to make sure that I was correct in assuming x is not big enough to matter, or x is small enough that I can ignore it. Yes, of the second ice table. So, because we moved everything over, we're no longer in that first set. Yeah, because otherwise 0.1 would be the smallest. But because we calculated, well, what if we started with everything over to the right as much as possible? I'm checking against these where I would actually subtract the x. Not everything. Now, this problem would be annoying if it was greater than 5%. There wouldn't be another way to do it on this problem. So yeah, if it was greater, then you'd have to do, you take 1.4 times 10 to the 14 equals 0.45 minus 2 times whatever I got for my number, 7.74 times 10 to the negative 5. And then that's squared, 0.775 minus 7 times and that's raised to the 7 and so on. So take that x, I would plug it back in. I would still have the 4x to the 4th because that's the x that I would still solve for. Actually, I'll just finish this finish this out. 2 times 7.74. So I just took that number that I calculated for x, plug it in for all those places where I assumed x was negligible. Yeah.
Okay. Is this more something basic? Where does exactly the 6 come from? I'm assuming that comes from the 4x to the 4?
Yeah, 4x to the 4.
'Cause
So, wait.
Is that 4 to the 4th power? Because
That's not 16. It's 256. No. You're right. You're right. That's 256. Doesn't change it by that much. Wait. Okay, so it didn't change it at all. Basically didn't change it at all. Oh, no. No, yep, nope, that's it. Bothers me a little bit, but so to see a problem where we did have to do that x where is the other one that I did? Oh yeah, here. So like on this one, we did the whole ice table, and then I got to this point, and I divided my x, I divided it by the smallest concentration, which we only had one here. We got 28.8%. That's not small enough to just use. And then I took that. So since this problem only has one x in it, really easy to just take this number, plug it back in for x, and recalculate x. So it looks like this. And then when I solve for that again, I get a number that's pretty close to 0.00288, but it's 0.00244. And then I compared here, I compared my number that I got before, or my number that I got here to the number I had before. Because what happens is when you repeat this calculation, it will fluctuate around some exact value. And so if you do it enough times, eventually it will stop changing and you'll get the same number every single time because you've kind of honed in on exactly what x is. Now, you don't need to do it that many times. Here, I got a number that was smaller than I got before, and so my percentage here is 84%, meaning that my new number is about 84% of the number I had before. If you wanted, you could do it kind of like a percent error. It's like 15.3% different. So I said, I want it to get closer, so I did this again, and I took now 0.00244. I plugged it in, right? It's the same calculation, but I plugged it in again with my new number. I calculate again, I got 0.00255, or 250. And now when I compare the number I got on the previous one, 0.0244, to the number I have now, it only changed by less than 3%. If I do it again, it'll change by even less. And at some point, it just stops being different. But 3%, if you want to use, this is kind of like the second 5% rule. If it's changing by less than 5%, when you do this repeat calculation, that's probably good enough that you can plug it in. But then unlike before where we didn't subtract, because I didn't actually completely finish this out, I do need to subtract that number because it's not less than 5%. It's still going to be like 25%. Any questions about ice tables? There will be at least a few on the test. I'll try to give you ones that can be simplified when possible or be done faster, but you do need to know what you're doing so that you're not spending a ton of time trying to refigure out how to do an ice table or equilibrium ice tables.